Good evening, everyone. I am Professor Balaji Rajagopalan from University of Colorado, Boulder. Firstly, I want to extend a hearty thanks to the Korean Water Association for inviting me to give this talk. I'm really sad that I could not be there in person. I would love to have been there in person. I hope I will be able to join all of you in person. And in particular, I want to thank Dr. Jong Ho for all his patience, guidance, and help through this process. So I want to talk briefly in my allotted 20-25 minutes about Bayesian hierarchical modeling approach for modeling space-time hydroclimate variables and also extremes. And I'll focus largely on stream flow, but you can see the methodologies can be applied to a variety of variables. You have my contact email down at the bottom. Feel free to reach out to me. I know I'm not there in person, either giving the talk or being able to answer questions. I want to thank my recently former student, Alvaro Sandan, whose work I'll be presenting in this talk. Alvaro was my PhD student for almost 4 years. He completed successfully last July, and then he went back to Chile, where he's currently an assistant professor at Santa Maria University in Valparaiso. I've also had collaborations with Professor Lal. I'm sure several of you in this audience would know him. He was my PhD advisor, and then also other colleagues from India. So the motivation to look at hydroclimate extremes is pretty simple and quite obvious. I'm sure all of you are quite familiar with extreme precipitation, daily stream flow, droughts. All of these cause massive disruption to society, economic damage, and not to mention, in the case of floods and extreme precipitation, the loss of lives and infrastructure. And so this is a report from Swiss Re released in 2020 showing the uninsured losses from these hydroclimate extremes on the top left, and then the bottom right is the number of occurrences. And again, you can see that much of the losses is due to weather related, and they are from floods and extreme precipitation. I'm sorry, the bottom right is largely from natural disasters, and the top left is the total losses, total uninsured losses. Okay. And also notice the Colorado River Basin, which I'll mention briefly, shown in the top right, which is one of the big rivers in the United States, but the biggest river in the intermountain west of the United States, and a lifeline for much of southwestern United States, including cities like Las Vegas, Los Angeles, Phoenix, Denver, and other smaller cities. In the case of panning out worldwide, the impact of extremes, again, is quite obvious. You can look at what is there in the Indian subcontinent. The impact of extreme precipitation is significant in terms of flooded areas, which then impacting the infrastructure. And you can also see that in other parts of the world as well, the state of the extreme. So this is for 2 years, 2018, 2019, but you can see this in other years as well. Most recently, of course, the Pakistan floods of 2022, I'm sure you are quite familiar with. This is extensive flooding and major crop losses. This happened around August 30th of 2022. And you can see the almost the entire country, or 3/4 of the country, was declared a calamity zone after that floods. And this was a result of a massive precipitation event. The impact in terms of agriculture is also enormous. So you can imagine not just people impacted by flood, but after the floods, there is less agriculture, less food production, then leading to other socioeconomic issues like poverty, hunger, and so forth. So hydroclimate extremes are really, really important to study and understand because their implications, their impact is quite significant. This is, again, flooding in 2018, heavy precipitation in populated areas, southwest part of India during monsoon, combined with poor management. Okay. And something more close to my heart where my parents live, this is in Chennai, which is in the southeastern part of India. You can see at the bottom. This was 2015, one of the massive floods recorded in modern history. And this happened during November 24th to December 4th. This was during an El Nino year. You can see that in the sea surface temperatures. And again, combination of events, heavy rain combined with mismanagement of water resources led to release of water from all the reservoirs surrounding the city, resulting in massive flooding. Okay. So given the impact, and I'm sure there are instances in South Korea as well, where floods routinely impact extreme precipitation, floods, and other related hydroclimate extremes. To mitigate, what do we need? Two things. We need to understand how these extreme events come about. In other words, moisture sources, pathways, how meteorology and land surface, they interplay in producing these large events, extreme events. And then the second is how to model and forecast them. So that's going to be the focus of my talk today. Spatial and temporal variability of extremes, and then also how to develop skillful forecasts. I'll primarily focus on things we did in these two papers, but then I have a list of all the papers in the reference in the slide at the end, so you can get access to them. So we wanted to model these extreme events in a Bayesian paradigm. And the Bayesian paradigm is much more like intuitively what humans think, where you have a certain idea of the process or knowledge of the system, which you can call it as prior, and then you make some observations, combine the two to then update your prior belief and what is called posterior. And these models, data sets are fraught with uncertainty. So you have some data, you have some model, and you have some expert knowledge. And given uncertainty in all of these, how do we combine them and put them together? And that is where the Bayesian paradigm is extremely simple, elegant, and very attractive. Shown in the picture is Reverend Thomas Bayes. He was the person who introduced Bayes' rule or Bayes' theorem that we all read, that we all get introduced in basic statistics. And the idea is, you can write it in terms of conditional probabilities, which is what's shown in this Bayes rule. A given B equals B given A times B given times probability of A, and then so forth. So conditional rule, pretty basic standard probability. We have applied, now the question is, how do you take this simple Bayesian rule, Bayes rule or Bayes theorem, and how do you apply it to large models? Now, it turns out that the likelihood function, which is at the top, which is probability of the data given the model and the parameters, is very difficult to estimate if your model is quite complicated. And so much of the Bayesian was relegated to the realm of theory. And up until recently, early part of 20th century, when computing power became more prevalent, suddenly Bayesian models were able to be applied in a variety of problems of space and time. Here are some papers that we applied Bayesian recently to a variety of applications. Spatial extremes in Bracken et al. stream flow on Colorado River using hidden Markov, also in a Bayesian framework. Bayesian weather generator, Baygen, Verdin et al. Applying Bayesian logistic regression for Arctic sea ice modeling. And then precipitation extremes in space and time. Alvaro's one of his papers. And then spatial extremes of stream flow on a river network. So I'll touch upon these last two will be my main, but then you can look at these other papers where we applied this Bayesian framework on a variety of hydroclimate extremes. Again, I'll be more than happy to interact with anybody who might have questions or who's interested in applying some of these techniques to your own applications there. So the study region that I'm going to focus for the rest of my talk is Western India, the Narmada River Basin shown in this map, which is one of the rivers that flows west and drains into the Arabian Sea. All the other major rivers in India, the Ganges, Brahmaputra, and all these peninsular rivers, they all flow to the Bay of Bengal. So we have daily stream flow at 4 gauges, shown in this red, or actually 5 gauges here. And they covered 1978 to 2014. And then we also have gridded precipitation covering India on a quarter degree spatial resolution. So motivated by this paper by Devneni et al., Professor Lal was a co-author on that. We developed the Bayesian hierarchical network model to model flow on this 5 gauges. Okay. The idea is, one that can generate ensembles and also provide robust simulation of uncertainties and take advantage of the network structure to capture the spatial dependency. And the model at a high level can be thought of as the stream flow at any given location or gauge is some function of stream flow and other attributes above that gauge or the upstream gauge, and then so on. Right? So that's what is shown in pictorially or schematically in the bottom right map. So more specifically for this basin, we start with the first layer, which is data layer. So essentially what you would do is you assume data Q sub t, which is the flow at any given time or day, is gamma distributed with these 2 parameters, R and lambda. And note the subscript T means those parameters keep changing as a function of time. And the parameters R change as a function of covariates. So they change as a function of QT, superscript 2 meaning stream flow from the previous gauge. PT is the stream flow above the gauge in the watershed between the upstream gauge and this current gauge. And you can add other parameters, other covariates as well. Similarly, you can also have a model for R sub t. And the observation is modeled as a gamma distribution. Gamma is a positive distribution. And we do this for every single station or gauge. So Mandaleshwar, which is the point here, the second from the bottom, and then Sandia, which is the topmost gauge, and similarly for all the other gauges. So you basically have this first layer for all the layer 1, 2, 3, 4 for each of the 5 gauges. Okay. And clearly we have parameters beta, the coefficients, and then beta 1, beta 2, all the betas at each of these locations. They have to be estimated. Now, just this itself, that let's say if you look at just the layer 1 Mandaleshwar, we can actually model that as a GLM, no problem, right? It's gamma regression. Then you have Sandia, you can model that as a gamma regression. Problem is if you're modeling them separately, how do we capture that joint dependence or spatial correlation? So you won't get that if you don't model the all of them simultaneously, which means the beta 1, beta 2, beta 3, all of them have to be estimated jointly, only then you can get the spatial dependency. So this is the data layer is the gamma distribution. The process is these regression models to get a time varying parameters of the gamma. And then we have some prior distributions on betas are normal, prior distributions on the variances are inverse gamma. And then we have data, we compute the likelihood function, and then we obtain the posterior, which is basically PDFs of all these parameters. Of course, to get the likelihood function, we have to simulate them. And so that's where we use MCMC, Markov-Chain Monte Carlo. And so here is what is shown are the correlation or scatter plots of these different covariates, coefficients, beta 1 versus beta 2, beta 1 versus beta 3, and so forth. Notice that even though we fit the models separately and the betas are for each location, that when the MCMC simulates these beta distributions, it simulates them and captures some of the correlation between the parameters as well. So that is also another interesting and important side benefit. So here are some results for Handia, and you can see the observed flow versus the ensemble mean, and here is the correlation is 0.83. It's pretty good. This is on the observed scatter plot between different locations, Mandaleshwar, Handia, Hoshangabad. You can see that there's strong correlation between them, obviously, because they're all on the same network. And the right-hand side is the simulated values from the Bayesian model. And again, you can see the simulations captured the spatial correlation quite well. Then what we did, we took the last 2 years of data, 2013-14, and we set it out and fit the model on the rest, and then generated the flows for that 2 years. And here is what is shown. Red is the observed, and then the ensemble mean is shown in the dashed line. And again, the correlation is pretty good, 0.91. So basically, the hierarchical model is able to capture. We also compute a measure called the skill CRPSs, which is how well the distribution that is generated from the Bayesian model captures the distribution of the observed. And then we also capture another metric called ESS, which is energy skill score, which captures how well the spatial correlation is captured. That is called the ESS. And again, positive values closer to 1 means highly skillful. And notice that at all these locations, the skill is pretty good in the CRPSs and also in the energy skill score across all the locations. And this shows that the implementation, the model has converged. And so there's an R statistic. If it is less than 1.1, that means the simulations have all converged. So summary of this is model captures the median observed flow very well. We generate ensembles and then we pick the median. Scatter plots of the flows in the posterior median also show very good skill. And the skill scores compared to traditional linear model are higher. I didn't show that, but it's there in the paper. So basically what we have is a nice spatial hierarchical model to simulate flows at individual gauges on the network of a river, but generating them or modeling them simultaneously. And that paper was in 2021 Water Resources Research. The second natural extension is we can take the same Bayesian model, but then now incorporate information from a physical model. Problem is with the physical model, you drive it with, say, a forecast from your meteorological department. So you have a precipitation forecast, you drive the hydrologic model, you get a single, you get a single stream flow trace. Now, you want to get ensembles to be able to model risk-based. And what we can do here is exactly the same format, same structural model, Bayesian hierarchical model, but now you can incorporate covariates, which are stream flows from the physical model. So VIC is a physical model. And so you can incorporate covariates, and then you run the model. So everything remains the same. You have some additional betas that you have to estimate, but they're all estimated simultaneously. And so here is what we get. This is the best model with all the covariates. The bottom right, the correlation is 0.85. So pretty, quite good. And what we also find in this is that relative to just the physical model, we increase the skill. So top is the for all the flows, low flow, mid-range flows, and high flows. And the x-axis are different gauges. And what is plotted on the left-hand side is the correlation coefficient. And on the right-hand side is the bias percentage. And notice that relative to Wick model, the bias of the Bayesian model is very low, almost 0 and less. Same thing with the correlation. Relative to the Wick model, the correlations are much higher. So what it indicates is that by incorporating the physical model output, you can generate ensembles. And we also look at the CRPSs and other metrics such as reliability diagrams. And again, we get very good CRPSs and also good reliability. You want the ensembles to be having a uniform distribution, and that's what you see with all of these at these different locations for different flows: entire flow, low flow, medium, and high flows. And you can notice that for high flows in particular, which is of interest for flood, we have a very strong uniform distribution. So we also incorporated this for forecasting in real time. So essentially we took real-time forecasts of precip, drive the hydrologic model in real time for next 5 days or 6 days, and then put them in this Bayesian framework to generate ensembles, right? And so same model, but now the Q will be these the forecast stream flow from real-time precip. And this is also a paper in Earth's Future. It appeared last year. And again, what we want to draw your attention is that there is a very good skill. The purple is the skill from the Wick forecast. So what is shown is CRPSs. The orange are the Bayesian combined model forecast. And then the purple is just the Wick model climate forecast. And notice that after 2 or 3 days, the Wick model skills are low, whereas the Bayesian model keeps up the skill for much longer time. So that's, again, goes to show that the framework is so general, you can incorporate covariates and other information. So BMC captures most of the observations, and this was for the 2021 season. Last year, we implemented it in real time, and you can see that we are able to capture the real-time variations quite well. Then lastly, how to incorporate or use this framework to model seasonal flow forecast. Okay. That is, take what's the maximum flow of the season at any given location. And here we use covariates such as El Nino index, the Indian Ocean dipole index, because we are trying to predict the seasonal maximum flow in the season at each of these 5 gauges, 1, 2, 3, 4 months ahead of time. So knowing that maximum flow means we can help in flood forecasting, flood mitigation, planning, and so forth. Okay. And we apply the same methodology, but now our upper level, instead of gamma distribution, we use GV because that's the appropriate distribution for maximum flow. And then the parameters of the GV, mu sub t, they vary as a function of covariates, which are the El Nino index, the Indian Ocean dipole index, and so forth. And so here are the various covariates for these different lead times. And these are the forecast versus observed. And this is the climatology. Notice that climatology will just give you a flat line, same value year after year. And again, here also, we find very good skill with CRPSs, certainly 0.1, 0.2. And notice that you're able to get this 1, 2, 3 months ahead of time. So pretty good useful skill that can be exploited for management purposes. So this paper is, we also looked at the number of events that exceed certain threshold, high threshold. And on that, we get very good skill. So we can tell not only what is the distribution of the annual or seasonal maximum flow, but we can also tell what is the number of exceedances above 90th percentile or 85th percentile. And those number tells you how many events you should be planning for. And so in summary, so these are all the references, and Dr. Jong Ho will have these, or you can also reach out to me. I'll be happy to share them. In summary, the Bayesian hierarchical model approaches on a river network offers attractive alternative for space-time modeling. Instead of modeling each location individually, you can model all of them together since they're all on a network. Quantification of uncertainty, information, prior knowledge can be incorporated. And you can combine this with seasonal forecasts, combine this with individual med service forecast. The extensions can be very good to paleoclimate, modeling spells. These are all things that we are considering. Water quality modeling, for instance. One can readily extend these if you want to know what's the exceedance of a certain water quality parameter, what's the maximum exceedance. All of those can be easily incorporated in this framework. So again, with that, and finally, Ministry of Earth Science funded this work, and Alvaro Asandan was my PhD student who worked on it, and I'm very thankful to him and several other collaborators, Will Kleiber, Professor Lal. So with that, thank you very much for your attention and for all the help and support.